Hi, Tim. Is that you?
Maybe after my season's over. Or maybe not.
Can you hear us okay, Tim?
Not bad enough.
Well, guys, let's go ahead and do attendance. Tim Hyde is who's presenting from INL, and it looks like he's here, but still connecting. Let's do attendance really quick, and then I'll make sure he's online and turn it over to him. So Hayden.
Here.
Connor. Still absent. Joe.
I'm here.
Okay. Marcus.
Here.
Okay. Porter. Great. Hell.
Here.
Great. Lynette.
Here.
Okay. Sam.
Here.
Okay. Tyson.
Here.
Great. Jack.
Here.
Awesome. Kyle. Amber. Great. Jennifer.
Here.
And Haley.
Here.
Great. Okay. Can you hear us, Tim? I see that you're connected, Tim, but we can't hear you. Hi. You are muted, Tim. Oops. So when Tim gets back online, he is the division director for fuel fabrication and nuclear material management at MFC. So he is over several buildings that the research focus is fuel fabrication. And he's got some slides to talk about the non-reactor facilities at MFC. Hey, Tim, welcome back.
I think I can hear you now. Something was wrong with my computer.
Okay, we can hear you and we can see you, so that's awesome.
Sorry
I
about
believe
that. I had to load Zoom this morning and it didn't work out so well.
Yeah, I've heard from a lot of INL people that Zoom is not very friendly to your computers.
Yeah, apparently not. Sorry.
That is okay. We have finished attendance and I gave a brief introduction. So we're pretty much ready for you to take over. You should be able to share your screen if you have slides. So I'll just kind of turn it over to you. I'm going to turn my video off just because sometimes multiple videos wreck the connection, but I'll still be here.
Okay, I'm going to try to share my screen, but I have a double monitor, so I'm not sure how it's going to exactly pop up.
When you click share screen, it'll let you select what you want to share. And you can share, like, for example, just the PowerPoint instead of the whole computer.
Uh-huh.
It should let you pick that.
Yeah, it's not even allowing me to do that.
I could also share them if you want to email them to me real fast. That's an option too.
Can you see that at all? No.
Do the video of you.
Yeah, it's wanting me to go through a security protocol. I'm assuming it's lab related stuff.
Okay. Want to email them to me and have me put them up on my screen, or?
At this point, that might end up being faster. Try it again and see if I can make it work before I do that. But
Okay.
yeah, it's apparently not going to allow access. Let me try one more thing. And if I disconnect, I'll log back in, but I'll try not going through the lab. I'll just go through my internet connection.
Okay.
Yeah, I don't see how to make it work. Okay, I just sent it to you. Sorry about this. I didn't have a solid way to test Zoom on my system.
We can get it worked out. I know that Zoom is not the best form, but not the best application for INL. We've had issues with several people
Oh,
INL trying to use it. It always does something.
well, apparently it's doing that again today, so. That file hit you yet?
Not quite. Looking for it. Okay, here it is. It. Then we'll share.
Yeah, you're more efficient than what I was able to do.
I have unfortunately had to isolate this last week, and so I've been teaching online, and it's not the greatest, but I've gotten pretty good at Zoom. So I don't know if Donna told you, but you're speaking to second year students. They'll graduate in May, who are, this class is kind of starting them on the job applying and seeking process.
Okay, yeah, I got a little bit of briefing and Scott Wallen showed me what he talked to you all about. This presentation, I can go a number of directions with it, but I'm going to try to focus on, I'll say, a fairly high level overview of the work that we do and the science objectives, and then ultimately the demonstration objectives for nuclear technologies. And again, because of the transition from some of these things are easier to do on a tour, and some of the pictures that I have may not give quite the right perspective. So I'll try to talk to that. But as we go through, and I'm trying to describe things, please ask questions, because without knowing everybody's background and what you've seen or where you've been, it's hard to, I'll say, get the right information to you. But that's what my attempt is here is overall tell you what we do at the materials and fuels complex, but that is integral with the overall nuclear research goals of the lab itself. And so there's going to be some of that intertwined with this discussion. Go ahead.
Have been to INL. We had a tour last semester, and we saw all of the reactor facilities and briefly walked through HFEF, but they have not seen the non-reactor facilities you guys have up there.
Okay. Well, then that's helpful to know that you've got that perspective. And then, so with that reference in the pictures that you can see now, that center picture on the right is through a window of HFEF. But to give you somewhat of a different perspective, the upper picture with the individual with the NOMAX suit on and the shield, and then the glowing, that is specifically within one of my facilities within my division. And what he's actually doing is heating up a billet of uranium alloy, and that's what is glowing red there. And he will swing that into place behind him near the orange area and extrude it. So actually like a uranium toothpaste, if you will. And that's one of the ways we fabricate fuel. The lower picture is in a facility called the IMCL, the Irradiated Materials Characterization Lab. And that is a couple of scientists that are working on, admittedly, I'm not 100% certain of the instrument, but probably an SEM, trying to elicit data out of the sample that they've got inside of that. Go ahead and jump to the next slide. So you probably have had some of this, but to give you some of the background relative to the materials and fuels complex, it started clean back in, as you can see in the slide, in the late 50s under the Atomic Energy Commission, which was what the Department of Energy was known as back then. And the two initial facilities that were built were the EBR2 reactor, which was inside the dome that you can see there, and then the fuel conditioning facility, which is a hot cell facility that is, at the time, was effectively integrally attached to the reactor dome so that irradiated fuel could move back and forth between the reactor and the hot cell itself. That program, as you can see, you know, from 61 to 94, that reactor did an extensive amount of work. There was a lot of data that we still find valuable today that was done during that time frame. And now we're staged to go from that to hopefully demonstrating some of the next series of reactors. Go ahead and jump. Next slide. So this is an aerial view of MFC. You can see far off in the background the treat or the transient or the treat reactor, transient test reactor, which based on what you said you've been to, and then the NRAD reactor is within the HFEF facility, which is the little sub picture in the upper right that says post-irradiation exam. The give you a scale of what goes on here. Pre-COVID, when we were fully operational, there was between 800 and 1,000 people that come to work at MFC each day. And they range from the guards that need to be there because of the nuclear material that's present, through the technicians, all the way through the scientists. And because it's effectively a mini municipality, so a little city out in the desert, you've got all of the infrastructure you need to support people living out there for part of the day. So anywhere from, you know, water, sewer, food, etc. So that gives you a little bit of background about what is there. Numbers of people wise. If you start in the upper left, you can see the transient testing. That's out at treat. And then going counterclockwise, the space nuclear power and isotope technologies. You may have had some reference, because I know it's been at least in the local media and the paper, that the INL assembles plutonium U2 or plutonium 238 based power systems that then go into NASA missions. And there was one just recently launched this summer that did contain a power source that was assembled and fabricated at the Materials and Fuels Complex. That's generally not part of our research cycle, if you will, but because of the knowledge in nuclear material and because of all the things that the infrastructure that is around, the INL and MFC is integral to that overall process. To get that power source into space. The overall program actually involves other national labs, Oak Ridge National Lab, Los Alamos National Lab, because it's actually a national effort to be able to create and then separate and fabricate the plutonium 238 that is needed for those systems. Jumping to the next one, the fuel fabrication and nuclear material management, that is specifically my division. And what you see in that image is an individual using an arc melter to make a alloy, a metal-based alloy for nuclear fuel, and his hands are in a glove box. And so that's what you see. And if you aren't familiar with an arc melter, it's a modified welding technology. So you control the gap and ultimately produce enough heat through the arc to melt metals. And that's a good way to make alloys, especially on a research scale. So smaller quantities, something 50 grams or less. Within my division and the way the arrow points, it kind of comes across the white dome with the flat roof on it, or the top hat on it. That is the zipper facility, ZPPR, in which there used to be a test reactor in there that was called the zero power physics reactor. That's been removed, but that whole complex there has significant quantities of plutonium and uranium. And how we use that is it gives us access to materials that a lot of people don't have access to. So we can use it for research purposes and ultimately, hopefully, demonstration purposes for new reactors. The next slide, the analytical research labs. There is the facility out there in which we need to do full elemental and isotopic analysis. So if you create an alloy, you want to know how much, did you make it right? Did you get the right amount of zirc in it? Did you get the right amount of uranium, what have you? And so that's where the analytical research laboratories come in. The individual to see in that picture is putting his hands into a shielded glove box that is actually attached to a hot cell. And that's done because also one of their important capabilities is to do that same kind of evaluation once something has been irradiated in one of the reactors. So our overall goal is to try to understand how fuels and materials perform under irradiation. So you got to understand how they behave before you irradiate them and after. The next slide, the fuel reprocessing and waste technologies. That gentleman is using a manipulator in front of a hot cell window, or in the hot cell that's the fuel conditioning facility. They do at this time a lot of work reprocessing the fuel that did drive the EBR-2 reactor for those decades, ultimately with the goal to have some of the product be a waste form that it has a reasonable disposal path, but also recovering some of the useful uranium and with the correct U-235 enrichment such that, and I'll talk about this a little bit in the next couple slides, but we're starting to get more and more interest in building new reactors and testing them out there. And we're going to need fuel for those reactors that does not easily exist throughout the United States or throughout the Department of Energy complex. So part of what that facility's mission is to start to create some of those new, or some of that new feedstock. The next slide, the characterization and advanced post-irradiation exam, that is generally associated with the irradiation and or the radiated materials IMCL facility, and it has significant instrumentation in it, down to very small length scale. So basically you use the instruments in there to continually increase the magnification at which you're examining something so that you can completely understand microstructures. Where did elements move? Where did fission products move? Things of that nature during irradiation. So go ahead and jump to the next slide. And I would encourage, if I'm the detail, please give me some feedback on what you're interested in. So ask questions as I'm talking here. So the biggest thing with this slide to try to point out is if you look at the gain and then that main text block that talks about technology readiness levels, the materials and fuels complex and the INL, if you start on the left side where it says proof of concept down in, or a 1 and a 2, I'll say that's the science. So somebody comes up with a concept, and can we test it and understand whether we think we're going to get the right kind of behavior out of something before you start to go into the larger scale. So that would be what we would call the R&D test bed. Investigating things on a smaller scale and then seeing whether it's worth trying to make larger and larger facilities or larger demonstrations out of it. So the transition then, as you go to the right, is the demo platform or the demonstration platform. And we believe a key value of the Department of Energy and BEA for nuclear options for the future is we are where things should be built and tested before they go commercial. And that area right now, with the funding and the external investments from venture capital interests in developing new nuclear technologies for commercialization, as well as a military application, is starting to expand quite a little bit. So we're trying to prepare for, in the next several years, building new reactors and being able to test them and see how they're going to really perform on that industrial scale. Go ahead and jump to the next. So this slide is one of the about as concise a way as we've come up to be able to communicate our overall research and, as it says, development and qualification activities that are performed at the INL, and then specifically the ones that the materials and fuels complex have checks by them. But if you start in the upper slightly left corner, you see advanced fuel design. And what you see there is, I realize it's small for everybody, but examples of 3 different fuel types. There's a particle fuel, and that's the sphere that in this case has actually been cracked, but that is some uranium material in the center, and then there's layers of carbon and silicon carbide to form that fuel type. The next one to the right is a plate type fuel, which is a sandwich of a fuel foil or fuel particles sandwiched in aluminum. An example of a reactor that uses that is the advanced test reactor uses that kind of a fuel. And then the lower ones are rod type fuels, which are simply at a simplistic level, fuel slid into a tube and then that tube is sealed shut. There's a lot more to all of those, but that's the details that the science and the things that we work on. So then as you jump clockwise over to feedstock preparation and characterization, we try to maintain the capabilities, and a lot of these happen to be in my division, to have uranium, have plutonium, have americium, whatever we need to produce a fuel. But we also need to be able to, not everything is a metal. Some of these fuel systems are oxides, other intermetallics, nitrides. So you've got to be able to do the conversions of a lot of different fuel forms potentially in order to do the testing. Then the next block talks about ceramic and metal fuel and material fabrication. And again, that is largely within my division specifically. And like I just alluded to, that in the feedstock form, you need oxides, nitrides, metals. Well, then you also need the subsequent facilities and processes to be able to turn those into pellets or rods or foils, whatever is needed for that specific fuel type. What you see there, that individual is in their anti-contamination clothing, but they're actually working on a lathe. And that lathe in this case is directly machining a uranium alloy. So we do, a lot of the experiments require very precise machining and fabrication. So it's not uncommon to have things that we have to hold a thousandths tolerance on to get things correct. And so that's why we have in my division some CNC controlled processes to get us that level of precision. For fresh fuel characterization, the next block mentioned earlier relative to the analytical research labs, it's important that we understand all of the characteristics of our fuel before it goes into a reactor. So I mentioned the elemental and isotopic analysis, but you also need to know thermophysical properties. So how much heat is it going to retain? How does it conduct heat? How does it expand as a function of temperature? All of those properties are important. And so we have a full range of instrumentation, a lot of which is in a glove box. And that's the picture you see there is an individual working in a glove box. To fully understand those kinds of properties, again, before it ultimately goes into a reactor for irradiation testing. Out of pile testing refers to what we refer to areas where, well, in order to fully understand how a fuel or a material is going to behave in a reactor, you also need to understand how it might behave under similar physical conditions without the irradiation and the neutron flux. So how does it behave at high temperatures? How does it behave at high temperatures in a molten salt? How does it behave at high temperature with an oxidizing atmosphere, things of that nature. And there's also places at universities and other national labs that we can irradiate our samples with non-neutron radiation, so ion irradiation. So send it to a university and hit it with ions for a period of time. And then there's a lot of information that can be gleaned from that, because ultimately putting things in a neutron environment are expensive and the details are, I'll say, more critical than some of the other ion irradiation techniques. So then going around to the bottom, irradiation testing. If you guys have been to ATR, ATR is at this point, and that's what that is, a picture of the core of the ATR, is our largest steady state irradiation testing vehicle. We do other send samples and experiments to other reactors across the world, but in general, that is where probably 90% of our experiments go, is to the ATR for steady state irradiation. And the periods of time that an experiment may be in that reactor can range from 6 months to several years, just depending on what the goals of that particular experiment and what information is trying to be elicited out of that. And you probably already know, although we've, a lot of the positions in the advanced test reactor are used for research associated with the Navy's nuclear propulsion systems, i.e. their reactors that run their submarines and ships. So jump into the next slide, which is the transient testing, which is treat, which is sound. Oh, sorry. You can go back. I'll finish going around the part of the reason the transient testing is important is you need to understand how a fuel is going to behave where there's an upset condition potentially. So steady state, but what happens if there's a spike in neutron flux? What happens if there's a spike in neutron flux and a spike in heat? So that overall can tell the full story for fuel qualification, because in order for something to be running a reactor, you really need to fully understand it from a lot of different angles and be able to validate and go through the licensing process to, I'll say, get permission to run that reactor. And so transients are important in that overall data package. Then the post-irradiation exam is primarily, the initial place is the HFEF hot cell, which it sounds like you've seen. So experiments come in there. They do what exams can be done inside the hot cell, and then they start to break the experiments apart, getting down into the fuels and the materials themselves. And as things get smaller, then their radiological hazard can drop. And then those smaller pieces can then be sent to other facilities like the IMCL and further examined with lower length scale instrumentation versus what you can do bulk in the hot cell. Then the performance assessment, basically that is where, when you understand what it was like before it went into the reactor, now you understand or have data what it's like after it comes out of the reactor. Did it do what you thought it was going to do? And then ultimately that information is fed back into the loop, and then you make adjustments based on, the information that you've gleaned, and i.e. because you're smarter, you do things better the next time. And then if you look at the center section there, the multi-physics and the modeling, and then referring to the government, basically the next cycle, if you will, is influenced by our computer modeling. How does that match with the experiments? How do we adjust? Are there things that we can do based on modeling that we believe will shorten or improve things? And then ultimately, we're all susceptible. We at the Department of Energy are susceptible to what the government and other entities are willing to invest in us and the technical areas that they're interested in looking into. So that's a pretty high level overview of all the things that go on at the materials and fuels complex. Is there any questions or You know, is this the right level of interest? Give me some, what would you like to know about those things? I mean, I have follow-on slides and I can show you some details of each one of these things.
I think it would be great if you could share with the students where in these processes operators get involved and what operators do in your facilities to support these missions and this research.
Okay, let's do that. Go ahead and jump to the next series of things and I can talk through some of that, maybe with some different images. So these images here are, as it says, it's fuel feedstock of a number of different elements, and how we do this kind of all of these, in this case, all of these processes are done in glove boxes. And it's done by a combination of technicians, operators, and the scientists. In my division and in a lot of the other divisions, excuse me, people work side by side, independent of their, I'll say, educational background or their title, be it via technician, engineer, or scientist. And where a lot of the hands-on work comes in for this area in my division is there's some challenges when you set these things up in glove boxes. It's one thing to do it on a bench top. So when you transition into a glove box, we do use a lot of technical expertise from our technician staff to, well, let's test it on a bench top. And then based on our experience, we know we got to adjust this or put a bigger handle here or something here so that when we do put it into a glove box, it's much easier to function and operate. Go ahead and jump to the next slide. So the perspectives that you can see here, again, is a range of a couple different fuel types that you see on the right side of the slide down to those rods. But the facility that you can see in the upper left is a facility that is within my division. And inside that, well, there's a reason that the fences are there is because of the quantity of nuclear material that are inside that facility. So that is a component of what we do relative to clearances. And so the people that perform work in that building, there is a lot of operators, to use the words that you, Mackenzie, you talked about. There's probably 10 operators that work in that facility, several engineers, and then the facility managers. Everybody in that can go in and out of that facility has a Q clearance. And then we are also on a program that's called HRP, Human Reliability Program. So we are subjected to significantly increased random drug and alcohol testing, and then yearly psychological and more in-depth physical exams than the average employee. And that's just the process that we have to go through to allow access or validation that people can be trusted to be around that quantity of nuclear material. The next picture that's more or less in the top center is a glove box line that is in that fuel manufacturing facility. And that gives you a little bit of a perspective where the work occurs through those glove ports that you see. Those are the circles. And that length of that particular lab is 30, 40 feet long. But there's numerous ones in that facility and in other facilities that are similar. And that's kind of the reference point that you see in the bottom there, the middle picture. That middle picture is of another one of my facilities. And that's the extrusion process there that I mentioned in the very first slide. That individual that was by the glowing would be to the back of the facility, almost dead center in that particular picture that's here. And then the extrusion press is that line that's on the right there. And then the pictures below are a furnace system. So it's the ability to heat and melt uranium, in this case, uranium alloys, and then cast them into whatever it is that we need. Again, all of the work that goes on in those facilities, setting up those systems, running those systems, is a combination of technician and engineer. Go ahead and jump to the next slide. This one doesn't talk to it too much, but all of the characterization work is actually a combination of technician and scientist. This one doesn't have a lot of stuff relative to, I'll say, the traditional mental picture of what a technician would do or an operator. But to run those facilities takes operations expertise, and moving samples and helping some of the scientists also always takes some sort of technical assistant and technician support. Go ahead and jump to the next slide. So again, although it's referenced to the out of pile testing, but you can see examples there in the center of more glove boxes. Again, that creates a very, I'll say, unique, challenging work environment compared to what would go on at a lot of universities. And that's just because dealing with the materials that we deal with and the hazards, you've got to do the work in a glove box versus a traditional lab space. And again, all of those things take technician expertise to be able to use the systems, get the systems in glove boxes, get them in those kinds of environments. And then you've seen other pictures, but the lower picture there is that happens to be a mini hot cell that is a 2-position hot cell that happens to be in one of my facilities in my division. And again, that takes technician support and know-how to be able to run those. That particular hot cell runs experiments, as you can see, a radiation-assisted stress corrosion cracking. What that means is that in the US's and the world's operating nuclear reactors, a lot of materials that are just outside the core and in some cases in the core experience significant neutron flux, and that impacts how those materials behave over time relative to cracking and failing. So the experiments here are designed to fully understand those materials better so that we can advise the actual operating reactors when they need to replace certain components. Another potentially, given where we are living now, those particular hot cells were actually fabricated at Premier at this point quite a few years back, but those were significant. They had a significant amount of those were actually made locally. Go ahead and jump to the next slide. You've been
We are actually just about out of time.
Sorry.
Up to some student questions. Do you want to quickly go through the last slides? What would you like to do?
Let me go ahead and jump through the slides and see if there's something that I might be helpful if I talk to, and then they'll just open it up to questions.
Okay, you want me to go to the next one then?
Yeah. So there's nothing, that's just the inside of the hot cell. And you've seen HFEF, and HFEF is run by, largely operators. You can see people again running a hot cell in there. go ahead and jump through trying to refresh myself if there was something that might make more sense to somebody from your all's perspective. I guess not. I mean, one note thing here is right at the moment, that SPL facility that is there, that facility is literally under construction. And that will be a new facility that has hot cells in it that, again, are going to need a wide range of technical expertise from operator, technician through scientist to run. So I'll open it up. Go ahead and what questions, or did it elicit any questions?
On a couple of your slides, I saw the phrase TerraPower. Is that the Bill Gates TerraPower or something else?
No, that you are correct. It is the Bill Gates TerraPower. He's the primary financial backer of TerraPower, but not the only individual of that scale of resources. But yes, that is that entity.
Thank you.
And they are continuing to look at EBR2 type fast reactor technologies. And then they now have a thrust to look at molten salt reactor technologies that are all underneath TerraPower. Any other questions?
Yeah, so what kind of qualifications do you need for the radiation assisted stress crews? So
Okay, I couldn't hear that very well. I could hear qualification, and then it sounded like a radiation assisted stress corrosion cracking. Is that?
yeah, to work with those cells, what kind of qualifications do you need?
What kind of qualifications do you need to work on that?
Yeah,
In terms of a qual for, I mean, we do, if I understand what I think you're asking, for the individuals doing that work, we do go through a training process, for somebody to be able to run those, whether it's a glove box or a hot cell. And depending on, at least within my division, the qual time, is anywhere from months. Well, it's months. It's never probably more than a year in which you'd be running any number of different processes. Sorry, I can't hear real good, so I'm trying to anticipate what the question really was.
We just covered radiation assisted stress corrosion cracking in one of our classes. So I think there was some particular interest in just what kind of work and what qualifications you have to be to work at that facility you showed with the mini hot cell.
Okay, the people that for that specific stuff, like I said, again, it's a range, and I actively try to maintain a range of education and experience backgrounds in my division. So there are operators that run the facility, and there's operators that put their hands on those manipulators as well as help support the samples coming in and out. So they're highly radioactive samples. So that process itself is quite tightly controlled. And there's also scientists that work on that. So wide range, I guess. Any more questions? I guess for maybe helpful background, my division is very much a hands-on division. I put significant value in people that are good with those kinds of skill sets, whether it's, I'll say what I perceive of your background going through what you're learning down there. Quite frankly, I've had good luck with people that grew up on farms, knew how to fix things, could jump into things, you know, whether it happened to be mechanical or electronic. A lot of my engineers are, again, hands-on associated engineers. They understand how to dig into things and make things function and work. So, like I said, I guess the biggest thing is I do put a high value on people's ability to perform work directly, and that's independent of their title or their educational background. Uh-oh, puppy involvement.
Whenever they move, they kind of break my little background. Any other questions, guys? Anyone online? Did you have a question? Okay. Well, thank you very much, Tim, for taking the time, especially on short notice when Donna couldn't make it. We really appreciated the information. I think it was really good for everyone to kind of see how the overall picture of INL fits together, not just with the reactors. So thank you very much.
Yeah, no problem. I hope it helped and was valuable.
Definitely. And if you have any more questions, I'll go ahead and end the Zoom for us. All right. Have a good weekend.